Back to the channel. Today, we are diving into the hidden heroes of the engineering world. Have you ever looked at a massive skyscraper or a complex machine and wondered, what actually keeps it all together? The answer isn't just massive beams, it's the small joints and brackets connecting them. Today, we're talking about how brackets define structural reliability in a complete why, what, and how guide to force distribution. Trust me, it's way more exciting than it sounds. Think of brackets as the traffic police of physical forces. When a heavy load travels through a structure, it needs to go somewhere safely. Brackets handle this by creating efficient force transfer. If a joint isn't designed right, you run into failure risks like incorrect moment loads or shear stress. Basically, things bending or slicing where they shouldn't. Brackets ensure the joint is just as strong as the beams they connect. So, what exactly are they fighting against? The dreaded point load challenge. Imagine pushing down on a piece of paper with a sharp pencil versus a flat book. The pencil will poke right through. That's point load risk, local deformation at fragile joints. Brackets act as load spreaders. They take that sharp force, distribute it over a larger surface area, and use precise engineering geometry to manage stress concentration so the metal doesn't get tired and snap early. Now, brackets aren't one size fits all. They come in an awesome variety of shapes depending on their job. First, we have angle brackets, which provide simple 90-degree reinforcement against pulling or cutting forces. Then there are gusset brackets, which add a cool triangular plate to give extra bending stiffness. Cantilever brackets are fixed at just one end to handle overhang weights. And finally, custom machined brackets use crazy specialized geometries for high-tech industries like robotics and automotive. But a great shape is nothing without the right material. Choosing the right metal is a balancing act between stiffness and weight. For instance, A36 structural steel is heavy but super dependable for massive buildings. If you're building a plane or portable tech, you might jump to 6061 T6 aluminum because it's incredibly light. For harsh marine or food environments, 304 stainless steel keeps things clean, while carbon fiber composites offer massive strength at a fraction of the weight for racing cars and drones. How do engineers actually calculate all this to make sure it doesn't fall down? It all comes down to the laws of physics and static equilibrium. To keep a bracket perfectly still and secure, three things must equal zero: the sum of horizontal forces, so it doesn't slide away, the sum of vertical forces, to support the actual weight, and the sum of moments, so it doesn't twist or rotate right off the wall. Before building anything, engineers sketch out what's called a free body diagram. It's basically a map showing all the invisible forces at play. They map out the applied load coming from the machine, the weight of the bracket itself, the reaction forces pushing back from the bolts or welds, and look closely at the moment arm to see exactly where the bracket is most vulnerable to bending out of shape. Once they have the map, it's time for the math. Calculating stress tells us exactly when a material is going to reach its breaking point. Engineers look at normal stress, stretching or squeezing, shear stress, slicing across the bolts, and bearing stress, the crushing force inside the bolt holes. They pull it all together using a formula called von Mises stress to predict exactly when the metal will start to permanently deform. Because real life is full of surprises like unexpected heavy weather or material flaws, designers always build in a factor of safety. This means making the bracket multiple times stronger than it actually needs to be. As you can see, lifting and public structures require the highest factor of safety because people's lives depend on them, while aerospace applications keep it a bit tighter to save crucial weight while staying perfectly safe. Once the bracket is engineered, how do we attach it? The attachment method changes everything. Bolted joints are great but need precise torque to make sure friction holds them tight. Welded joints are incredibly strong but require rigorous non-destructive testing to ensure the weld penetrates fully. And a rising star is adhesive bonding, which is becoming super popular for modern carbon fiber composites because it leaves a perfectly smooth finish. We are living in the future of engineering, because today, computers can actually grow brackets for us. This is called topology optimization or generative design. Instead of standard geometric shapes, an AI algorithm figures out exactly where the stress lines flow through a part. It places material only on those lines, resulting in beautiful, organic shapes that look like nature and are 30% to 50% lighter while keeping the exact same safety ratings. At the end of the day, This rigorous analysis is what ensures long-term reliability in the machines, vehicles, and buildings we use every single day. Taking the time to calculate force requirements and run structural validations means the world keeps spinning smoothly and safely. To recap our journey today, we looked at how force transfers efficiently, how we manage tricky point loads, and why mapping internal load paths with free body diagrams is so essential. We also covered selecting the perfect materials and calculating precise safety factors to prevent failure. Thank you so much for watching. If you love seeing how the invisible world of engineering shapes our everyday lives, make sure to hit that like button, subscribe, and let me know in the comments what component we should explore next time. See ya!